So today we're going to learn how to write the electron configuration for different elements in the periodic table. Last class we talked about how if we want to understand how atoms behave, we have to know how their electrons are arranged. And so how we do that is by electron configuration. So when we write electron configuration, we write the shell number first, and then it's followed by the subshell, which is either that S, P, D, or F letter. And then the total number of electrons are superscripted on each subshell. And then we'll keep filling levels until we run out of electrons. So for example, helium's electron configuration is 1s2. So it's in the first shell, the S subshell, and it has 2 electrons. Sodium's is 1s2, 2s2, 2p6, 3s1. Now if you notice, sodium has a total of 11 electrons. And if we count up all of the electrons, it should also add up to 11. So there's 2 in the 1s, 2 in the 2s, 6 in the 2p, and 1 in the 3s. So if we add up 2 plus 2 plus 6 plus 1, it equals 11. So this is how we account for all 11 of sodium's electrons. And then finally, here's bromine. Bromine's configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. So in order to learn how to write electron configurations, first we're just going to start with, well, how do we divide up and organize the periodic table? So the periodic table can be divided into different sections. So these first 2 columns, we call this the S block. And then this section over here, we call this the P block. This middle section is the D block. And then the bottom 2 rows is the F block. So the first thing you should do is grab a blank periodic table. And on your periodic table, you need to color in each block. Okay, so kind of look up here. You see how there's a key, so pick a color for S, and then you'll shade in the first 2 columns for S. Okay, pick a different color for P, shade those in, then do D, and then do F. Then you're going to label your rows. So notice in the S block, it goes 1S, 2S, 3S, 4S, 5S, 6S, 7S. And then in the P block, it lines up with the 2S row, so it's 2P, 3P, 4P, 5P, 6P, 7P. And then in the D block, the first row starts at 3D. So it goes 3D, 4D, 5D, 6D. And then in the F block, it's 4F, 5F. So once you color your blocks on the periodic table, go ahead and label what each row is called as well. So now that we have labeled our periodic table, we know where the blocks are, and we know the shell numbers. Now we're going to look at 2 different ways that we know how electrons fill in those shells and subshells. So here's the first option of how to remember. So if you looked at your periodic table, in the S block, it went 1S, 2S, 3S, 4S, 5S, 6S, 7S. Then the P block started at 2P, and we put it on the same row as 2S. So 2P, 3P, 4P, 5P, 6P, 7P. For the D block, it started at 3, so we put it where the 3's are. So 3D, 4D, 5D, 6D. And then the F block started at 4, so it goes in the same row as the 4, so 4F, 5F. So then if we put it like this, it kind of looks like a triangle. I'll outline what I mean. Right, it's like this shape, kind of makes like a triangle shape. And then if we just fill in the rows with these like bottom diagonal pointing lines. So we go from this direction. This is the correct filling order. Okay, so we go from 1s2 to 2s2 to 2p6 to 3s2 to 3p6 to 4s2 to 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2 to 5f14, 6d10, and 7p6. Okay. So this is one option to remember how we fill in electrons in their shells and subshells. Another option is to just read the periodic table like a book. And this is actually the method I prefer. So again, if we start at the top and we go left to right, top to bottom, so it's 1s and there's 2 of them. Then we go to 2s, there's 2. Then we jump all the way to 2p and 1, 2, 3, 4, 5, 6, so 2p6. Next is 3s2. Then we go to 3p6, 4s2. Then we have our 3d10, 4p6. Then we have 5s2, 4d10, 5p6. We can do 6s2. Then I would go 4f14, then 5d10, then 6p6, and so on. Notice how either method you choose, we follow the same filling pattern. So you can either go with the periodic table where you read it like a book, or you can use this triangle diagram and follow the downward arrows, but either way we fill in the exact same order. All right, so now we're gonna do a couple practice electron configurations together. So the first element we're gonna write the electron configuration for is magnesium. So first we just have to find magnesium on the periodic table. And then we always start at the top. Okay, so this is the first shell, and this is the S block, and it has 1, 2 of those electrons. So magnesium has 1s2. And then I keep going, so this is now 2s, and it has both of those. So it has 2s2. And then I jump over to the p section, and it's 2p, and it has 1, 2, 3, 4, 5, 6. It has all 6 of those electrons. So 2p6. And then we jump down to 3s, and it's 1, 2 over. So 3s2. Another way we should check is magnesium has 12 electrons. We get that from the periodic table. And if we add up the superscripts, they need to equal 12. So 2 plus 2 plus 6 plus 2 is 12. Now we'll do the same thing for chlorine. All right, so first we have to find chlorine on the periodic table. And then we're just going to do the same thing. We always start here. So it has 1s2, 2s2, 2p6, 3s2. Then we jump over. This is 3p, and it's 1, 2, 3, 4, 5 over. So this time it's going to stop at 3p5. And again, we can check our math. If we look at the periodic table, chlorine has 17 electrons. So then we should make sure our superscripts add up to 17. So we have 2 plus 2 plus 6 is 10, plus 2 is 12, plus 5 is 17. So all 17 electrons have been accounted for. All right, we're going to keep going and just do a couple more practice problems. So now we're going to write the electron configuration for silicon. So again, we just need to find it first. And we always start here. So silicon has 1s2, 2s2, 2p6, 3s2, and then 3p, and it's 1, 2 over. So we write 3p2. All right, next we have iron. So here's iron on the periodic table. So again, we're going to start at the beginning. So iron is 1s2, 2s2, 2p6. I'm going to pause and write that for now. So 1s2, 2s2, 2p6. Then it has 3s2, 3p6. Then it goes down to 4s2. And then this is the D block. D is n minus 1. So it's 4s, and then it becomes 3d. So now we just count over boxes until we get to iron. So it's 1, 2, 3, 4, 5, 6. So I'm going to write 4s2, and then it's 3d6. All right, and then the last one we'll try is gallium. So here's where gallium is located. And I'm going to start just like I always have. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And then now we get to the d, so it's n minus 1, so it's 3d, and it has all 10. So I'm going to write 3d10. And then after d, we get back to p, so it's back to our normal n number. So if it was 4s, it's 4p, and it is the first box. So I'm going to write 4p1. So electron configuration, it's useful like that. It helps us know like how electrons fill in their shells and subshells, but it can still be hard to visualize if electrons are paired up in an orbital or not. So we use something called an orbital notation or an orbital diagram that helps us see how many electrons are in an orbital. And this has to do with if atoms are willing to bond or not. So we use these boxes to represent orbitals. And then each box is going to be labeled with the shell number and the sublevel. So shell and subshell. And then the arrows are used to represent electrons. So hydrogen has a configuration of 1s1. So it's in the first shell and subshell, and it just has one electron, so there's one arrow in that box. Lithium has a configuration of 1s2, 2s1. So we see in the first shell and subshell, there's 2 electrons, and then in the second shell and subshell, there's only 1 electron. All right. Next, we have aluminum. Aluminum's configuration is 1s2, 2s2, 2p6, 3s2, 3p1. So we can see its diagram. So it's 1s2, 2s2, 2p6, 3s2, 3p1. So a couple of things I want to point out when we fill in these orbital diagrams. So when there's 2 electrons in a box, one arrow will always point up. The second arrow will always point down. And that is just to show that in an orbital, electrons spin in opposite ways. So one electron would spin clockwise and the other would spin counterclockwise. So how we diagram that is just showing one arrow goes up, one arrow goes down. And then the next thing is when we fill electrons in orbitals, I'm going to pick on the p section since there's 3 orbitals. Electrons fill in 1 electron per orbital first before they buddy up. And a good way to think of that is think about at your house. If you had a sibling and you had a 3-bedroom home, would you and your sibling share a room willingly, or would you take your own space? And so just like you, electrons want their own space. So they're going to take up their own space first. And then if you have more electrons to fill, you'll go back and you'll double them up. So the real benefit of these orbital notation diagrams is really seeing how many unpaired electrons there are. So aluminum has paired electrons as 1. So we know aluminum's going to want to bond. It wants to have a filled orbital. All right, so now that we've learned how to do full electron configurations, it's time to learn a shortcut. So we call this shortcut the noble gas notation. So what we do is any element beginning with period 3 or the 3rd row, we can use a shortcut, or we can use noble gas notation. So we're going to find the element that we're trying to write the electron configuration for. And then we have to locate the closest noble gas that comes before it. Okay, so it has to have less electrons than the element we're actually trying to write our configuration for. We're going to write the symbol of the noble gas in brackets. And then we'll just continue on with the rest of our electron configuration. So, for example, we'll start with chlorine. Okay. So if you look at the periodic table, the closest noble gas to chlorine that comes before chlorine is neon. So you're going to put neon in brackets, and by putting neon in brackets, that replaces neon's electron configuration. So it's replacing 1s2, 2s2, 2p6. And so then you can just pick up after neon. So after neon, we would go 3s2, and then to get to chlorine, it's 3p5. Next, I have iron. So if you find iron on the periodic table, the closest noble gas that comes before iron is argon. So we place argon in parentheses. And then we start after argon. So then we have 4s2, and then we get to 3d, and if we count over to iron, it's 6. All right, and then my last example is iodine. So if we find iodine on the periodic table, the closest noble gas that comes before it is krypton. So krypton goes in parentheses, or in brackets. And then we just pick up the electron configuration from there. So after krypton, we have 5s2, 4d10, 5p5. And then one thing I want to point out, noble gas notation has a really nice way of showing us valence electrons for representative elements. So that means not transition metals. Okay, so chlorine and iodine are my representative elements up here. And so valence electrons are always those in the highest shell number. So if we look at chlorine, the highest numbers we see is 3s and 3p. So if we look at those electrons, that'll tell us how many valence electrons there are. So chlorine has 7 valence electrons. And then if we jump over to iodine, so again, we look at our highest shell number. So there's 5s and 5p. So if we look at those electrons, and this one's also 2 plus 5, which is 7. Okay. So those highest shell numbers will tell us our number of valence electrons for our representative elements. All right, so now we're just going to do a couple practice problems of writing the shortcut or the noble gas notation. So our first element is calcium, and we have to find the noble gas that's closest to calcium that comes before it. Okay. So in this case, it's going to be argon. So we put argon in brackets, and then we just pick up right after argon. And so after argon, we go to 4s, and calcium is the second one over. So it's 4s2. All right, next we have bromine. So bromine is here. And we have to find the noble gas that comes right before it. So if we can't use krypton, it has to be before it. So we have to write argon again. And then everything after argon. So it'll be 4s2, 3d10, 4p, 1, 2, 3, 4, 5. 4s2, 3d10, 4p5. All right, and then our last one is krypton. So krypton itself is a noble gas. Unfortunately, you can't just put krypton in brackets and call it a day because we want to see those valence electrons. So you still have to use the noble gas that comes before it. So it'd still be argon, and then 4s2, 3d10, 4p6. And the reason why you have to write it out, you can't just put krypton in brackets, is we want to see those valence electrons, right? So our valence electrons are in the 4p and the 4,6. And so we can see that argon has all 8 valence electrons.